Hello, my name is Perla Garcia, and today I'm going to be talking for my long talk about spatial learning and learning strategies and memory in goldfish. So why is this relevant, or why should anyone care about this? Goldfish have this common misconception around them where people think that they're completely useless or ornamental, and we kind of see them as organisms that move around aimlessly. They don't really have a lot going on in their brain. And this is something that has caused them to be overlooked or underestimated when it comes to science and research. So, in this talk, I'm going to tell you guys why we should look more into them and how we have more in common with them than we might think. Me assuming that the general public doesn't really think that humans have anything in common with goldfish just because they're very small and they're aquatic. We're not aquatic, we're not small. But people have found that the telencephalon, which is an area in fish brains, correlate with the hippocampus. As we know, that's something that we carry in our brain. And because of this, fish can move to become model organisms in future research studies, which is something that I believe we can branch off into after further analyzing their brains and similarities that we might find between us and them. So I'm going to walk you guys a little bit through the brain structure of these animals. This picture up here is the top view of a fish, of a goldfish. And this part right here in the front, labeled TEL, that's actually the telencephalon, which is what we're mostly going to be focusing on today. OT stands for the optic rectum, and this is mainly just their peripherals, what they see. The CER stands for the cerebellum, and this is just so you guys can get an image in your head of what is really going on, because I don't believe everyone just Googles fish brains for fun, so we might not know. And this is the VL, which is the vagal lobe, and it just kind of contains primary sensory nucleus and motoneurons, which also kind of has to do with movement. But today we're only going to be focusing on the telencephalon. This is the inside of it, so you can just kind of get a sense of what it looks like without the telencephalon, which is what the scientists in the research study that I will be presenting to you have done. The focus of their research is to kind of prove the telencephalon's importance and how it is used for place and cue spatial learning. Their main question was they wanted to see what other methods would be used by the fish that have gotten their telencephalon removed, and how they would adapt without it, and if they could, just to see how important the telencephalon is for them, if at all. So moving on, I'm going to give you a brief walkthrough of what today's presentation is going to look like. We already went through why is this worth knowing. I talked to you guys a little bit about the brain structure, and we're going to move on to the experimental background of this research study. And I'm going to present to you the four-arm test tank, which is the environment that these fish were tested in. We're going to dive into some context analysis, and the importance of an intact talencephalon. We're going to talk about the fish's navigation efficiency, and at the end, we're going to conclude with their spatial cues and memory and how they were affected by this trial. So for the research background, this study was conducted by Lopez J.C. and some colleagues of his. This research paper was titled Dissociation of Place and Cue Learning by Telencephalic Ablation in Goldfish. And ablation really just means that part of their brain, as I showed you guys before, was just completely surgically removed. There was no real science behind the removal. It was just kind of cut off. And they're kind of testing those spatial strategies involving the telencephalon, that part of their brain. And we're trying to see if these goldfish, can learn how to live without it. And because we know that they can form complex map-like representations of the environment that they travel day to day in their brains, we want to see how they're going to be affected because of the ablation. The fish that were used in this research study were actually initially bought from their local pet shop, and after this, they were bred, which obviously gave these scientists stock tanks to choose their sample size from, which were randomly chosen. And then they performed the ablation in around half of them, and then the other half just remained untouched, no surgery whatsoever. The fish that were randomly chosen, all of them, they were allowed to explore the tank, and for around 3 to 5 days, and this is something that they called training, because they just let them roam around, familiarize themselves with the environment that they were going to be tested in. And at one end, it's a 4-arm tank, which is just a cross. And on one end of those 4 arms, I will show a picture later so you can get a better idea of what I'm talking about. But on one of those ends was some food, and there was no real there were no real recordings done of this, because it was just the fish trying to getting familiarized with what they were going to be dealing with. And the goal was to, like I said, find the food in the 4-arm maze. And before the experiment actually began, they were not fed for 2 days, which doesn't harm them at all. But they did kind of want to flush them out of any food and any smells that they might have grown accustomed to during training. So this is a better representation of what I've been talking to you guys about. This is an exact representation of where everything was positioned in the study room. Oops, sorry. This is the gray curtain that the scientists would hide behind just so they wouldn't intervene. The color of the curtains didn't really matter, but this one was gray, this one was white. Nobody was really on this side. They mostly remained on this side so they could get a good view of the animals, and they could get good data from it. And these were just random objects, just normal things that you would find in their experimental room. Nothing was really there on purpose, but the fish could obviously see these. So all this furniture kind of acted like the cues for the fish to be able to see, like, oh, the toys are here, maybe the food's over here. They kind of just used them to position themselves in the room, even if they were just inside of this 4-arm tank. So the arrows right here, this is kind of where training first began. One arm was cut off, so they couldn't really cross over here if they started from here and vice versa. But the goal was just to come over here and get to the food. And they did this, like I said, for around 3 to 5 days. And then all the fish were put through 3 different simulations, which I'll be going into next, just to test their memorization and spotting spatial cues, which, like I said, would be considered all these around the room. So how was the data measured? They did record everything, but they threw out the total errors, meaning that if a fish didn't move at all, they didn't record that. It's not really useful data for what they're trying to measure, but they did record if a fish went straight into which arm they went into. They would record like, oh, like he made a left turn immediately, they would record that. He made a right turn immediately, they would record that. They recorded the time. It wasn't really a determining factor, but it was worth noting. And they also recorded how many trials it took for them to actually get to the food. So this is the type A model, and like you guys can see, almost exactly like the training environment. Nothing was really blocked off. It was kind of like I said, exactly like the training. Only one arm was blocked off, but they could still see all these spatial cues. Sorry. So they could either turn left and get to the food, right, and then see, or right and see that there's nothing there. Maybe they would turn around, maybe they wouldn't, but that's something that the scientists would record. And here is the concluding data. So as you can see, I labeled which one was the intact and which one was the ablated. So these over here, depending on how dark it is how many more fish. So like if this one right here is darker, more fish went to the incorrect location, but the correct cue, meaning that they kind of memorized where they had to move instead of looking at the cues, which would be like the toys or like the bookcase and things like that. But the ablated, the telencephalon ablated goldfish, they also kind of went for the correct cue, but the incorrect location. And this isn't all that big of a, there's not really that much of a difference, but we can see that more of the intact went for the correct location, incorrect cue than the ablated did, meaning that the intact kind of went for either or, while the ablated did prefer to go for the cues. And we'll see more of what that means later on. This is type B, and in type B, they put a curtain around the testing site, and this kind of just completely deleted cues, which is what we can kind of see affected them a lot in the results. Here we can see that the intact went for the correct cue and they got to the food, and the ablated went for the correct cue and got to the food. So we can see that there's like a big difference between type A and type B. So like here we can see that they kind of went for either or, the intact, and then in type B, most of them went for the cue. And that can just kind of show us how eliminating the use of those cues can kind of make them try and remember and see their place in the environment, even if they can't really see the outside cues. And then just to keep the data a little bit more, to get stronger data, they would rotate the forearm tank just so they could keep everything fresh and have no like real bias affecting their data. So yes. And then in type C, everything is up for grabs. They can see both the outside cues and nothing is really blocked off. But here we also did eliminate the food, and here it was kind of more to test their memory, just to see where they would, the location that they would choose. So like if they turn left, if they turn right, and this was done after doing the type B trials. So they kind of had to like memorize where the food was in the previous trial, and then that's where they would go to this marking the correct location. And here we can see that the ablated, they were a little confused. The majority went to the right. This is where we kind of see the telencephalon's influence, because the ones that were intact, they chose the correct location based on the cues, based on memorization, both were available to them. But the ablated, like I said, they were confused. They kind of went everywhere. There was not really a stronger side that they would go to. So you can't really say that they went off memorization or cues, but because you can see the cues and the cues were there to help them, maybe some thought that it was closer to the toys, maybe some thought that it was closer to like the bookcase. Here's where we see that the ablated used cues more than the intact did. So a point that I feel is important to make, because of the data that we've analyzed, is that fish can simultaneously learn to use different sources of spatial information for their navigation, meaning that they can, even though they don't have their telencephalon, they still have a way to move around using those cues that we talked about earlier. But it's still not really beneficial, because obviously as an animal, you would rather have more to your advantage than less. So through the data, we can say that those fish that had the intact telencephalon would use both cues and location, because sorry, their data kind of showed that they used both. But when we saw the data of the ablated telencephalon fish, they leaned more towards cues. Like we saw in trial C, they were confused. They didn't really know where to go. Even if they did have the cues, they didn't have something to reassure them. There was no food, and memorization really didn't help them, because they were going kind of everywhere. Which is why, like I said, the fish that had the telencephalon surgically removed had to rely more on cues than anything else. And because of this, because we know how our hippocampus works, we kind of have gathered through this research paper that the effects of the telencephalic ablation affects the performance of the fish in spatial tasks, and it resembles the damage when there's damage to our hippocampus in birds and other mammals. So they're similar. As for navigation efficiency, telescopic ablation in the goldfish did cause a deficit in spatial tasks. We could see that from specifically from task C, because the ablated goldfish, they needed to use the environmental landmarks, but they still couldn't grasp the they couldn't memorize to so they could move where they needed to move. So they needed those cues and, like I said, the environmental landmarks. And this is very conflicting information because nature doesn't really, it changes a lot. So if there's a fish out there that is missing their telencephalon, more than likely would not really be able to get around the way that it needs to. So this is where we can kind of see that fish have that like spatial, they have multiple spatial memory systems that can increase their navigational efficiency, even with the environment's changing landmarks, because they can use those cues. So for my concluding points, so as we talked about in the beginning, even though fish have small brains and they seem to be very, very simple creatures, they can be used as model organisms. They're very interesting to watch compared to things like worms. They're bigger, so you can better analyze them if you need to. Like these scientists, they perform surgery on them. It's not really that, it's not very wise, I don't think, to do surgery on a sea elegant, something like a sea elegant that you'd have to look through a microscope to even touch. So they can teach us, these fish can teach us more about memory and spatial learning. And the conclusion here from the research paper kind of led us to believe that fish who have an intact telencephalon will use both cues and location when retracing their steps. And those that didn't kind of had to rely more on those cues over memory, which isn't really ideal. And like I had said before, the similar functions between their brains and their telencephalon and our hippocampus kind of suggested for these scientists that the evolutionary history in vertebrates has created some very crucial learning for map-like or spatial representations of the environment. And that is all for today. Thank you.